Welcome back. So in this video, we're going to look a little bit deeper into this frequency factor idea and explore some of the ideas of what we call collision theory. So collision theory is sort of similar to what we talked about when we talked about the kinetic molecular theory with gases. And it gets to the heart of when reactions occur, if there are multiple reactants involved, whether those reactants are the same or two molecules of the same thing or molecules of different things, right, that they have to collide. There has to be an actual collision. And when those reacting molecules collide, there is the potential for a collision. Now, with kinetics, sort of one of the ideas is that, okay, a lot of these collisions occur, but not all of them lead to product. Not all of them are what we call productive collisions. So, on average, an average reaction, we have about 10 to the 9 collisions per second, or about 1 billion collisions per second between molecules. Now, of course, this is going to vary with concentration, etc., but just as a nice number. Once molecules collide, they may either react or they may not, based on a couple of factors, right? And so the two most important factors here, and this is, ones that you really want to, sort of think about, is when these molecules collide, they must meet two things. They must have enough energy to collide, or to get from the reactants to the product, right? So there must be enough energy available to break the bonds holding the reaction molecules together. Now remember, this is what we talked about in the exponential factor. Right? That tells me the fraction of molecules that have enough energy to overcome the activation barrier. Now, the other factor that we don't take into account in the exponential factor is something called the orientation, right? So molecules not only must collide with enough energy, they must collide in the right orientation, right? In other words, the right atoms in the molecules must be near each other when they collide. So where does that come into play? So we revisit our Arrhenius equation, right? Remember, we had the frequency factor. And previously, we've just defined this as, right, the number of attempts to get over the activation barrier. But really, we can divide this into two terms. One of them is what we call the collision frequency. And this is essentially the way we've defined the activation, that we've defined the frequency factor previously, right? It is represented by Z here, and it is the number of collisions that happen per second. So in other words, the number of attempts to make the reaction go, or a number of attempts at the activation barrier. Now, there's another factor buried in this frequency factor called the orientation factor. So let's think about this. So let's say we have this reaction here, where we have two molecules of NaCl react to give you an NO and a Cl2. So it's not that these only must collide. They must collide in the right way. So, for example, right, if these molecules collide where the two oxygens are near each other, well, that's not going to really help us, because think about what has to happen, right? We're leaving the NO essentially the same, but the two chlorines are forming Cl2. So when these collide, we need the two chlorines to be close to one another. So if the two oxygens are near each other, or if an oxygen and a chlorine are near each other, right, nothing's going to happen. They're just going to kind of bounce off of one another. They become an ineffective collision. But when they collide with the two chlorine molecules close to one another, this is when we get an effective collision. So while we have a number of collisions, and right, of course, we want to try to maximize Z, right, the number of collisions, because as we saw back here, right, of course, the more collisions per second, the more collisions that have the potential to be effective. So we want to have more collisions, but only a certain fraction of them are going to be effective. Now, unfortunately, and the reason we don't dwell on this a lot is that we can't really do much about it. The orientation factor is a statistical term relating how often these molecules will collide with the right orientation. And for most reactions, this is far less than 1. Right? So, of course, if this was 1, that means every collision would have the right orientation. So, but for most molecules, when they collide, they're not always going to have the right orientation. The more complex the molecules are, the smaller this P term is going to be. So now, if we revisit here, we see that Z tells me the total number, and P is the fraction of those that have the right orientation. So now we can come back and say our frequency factor, right, is not just the number of attempts, right? It's the number of attempts with correct orientation. So the frequency factor builds in the orientation effect, whereas the exponential builds in the energy effect. So total number of collisions is important, but more importantly, some of those collisions are going to have the right orientation, many won't, so that's going to reduce the number of collisions that are successful, and some fraction of those will have a right energy, which we get from the exponential, which is going to further reduce the number of collisions that are productive. So while we may have 10 to the 9th collisions, many of those are not going to have enough energy when the collision occurs, and many of those are not going to be in the right orientation. So the actual rate or the number of productive collisions is far lower than the total number of collisions that we have. All right, so this sort of wraps up this section of the chapter. Now, in the last 2 sections of the chapter, we're going to look at a couple of different aspects of kinetics. The first one is going to be, or one of them I will say, one of them is going to be what we call the mechanism of a reaction. And so in that section, we're going to look in more detail about how reactions actually occur and sort of get rid of sort of the intro idea of here's my balanced chemical equation, put it all together, everything comes together and forms products. Right? So we're going to nuance that a little bit, get into a little more detail. And the other topic that we're going to address is the use of a catalyst in a reaction. How does that affect the reaction? What does it change, etc., in terms of working with our reactions?